11.2, I break it into two parts, part A and part B. In this section, we're going to talk about geometric series and telescoping series. Interesting name, isn't it? So first, let's talk about the definition. Last time we talked about sequence. A sequence is an order list of number. You just list them, right? You list the number in a certain order, and that is a sequence. Today, we're going to introduce a new definition. It's called a series. Okay, a series is the sum. Okay, it's a sum of all the turns in that sequence. So A1 plus A2 plus A3, and etc. Continue. Okay, so you sum them up. So don't confuse these two. Sequence, you just list the number, but series, you add the number. Okay. So that's the difference between them. Now, the definition over here, we also want to introduce something called the n-partial sum. N-partial sum is the sum of the first n turn. So you just add the first turn all the way to the n turn. That's called the n-partial sum. Why is it called partial? Because it's not the whole sum, right? The sum, you had to add the infinite many turns. So it's a partial sum. And it's called the n-partial sum because you only have the sum of the first n turn. And this is the notation for it, okay? And you call that Sn. S here for sum. And you only sum up the first n turn, so you put Sn, okay? So imagine that it's the sum of the first n turn. Now, after that, if you let n go to infinity, then if this n-partial sum go to a finite number, okay, so as those turns over here continue on, right, if you add more and more turns and you let n go to infinity, right, then if somehow the n-partial sum stabilize and then approaching to a finite number, then what happened over here is we call that the series over here converge, and it converges to that finite number. Now, it would be better that if we can use an example to explain this, okay? So this example here is a geometric series. So you add 1/2, add 1/4, add 1/8, add 1/16. In general, the general term for that series here is 1/2 to the n. So every time you from one turn to the next, you keep on multiplying by 1/2. So for the n turn, you have 1/2 to the n power, okay, like this. So what do you think? Do you think this series over here converge? Is it going to converge? Is it going to be a finite number? You want to look at the picture? Huh? You think so? Okay. All right. So let's try to visualize this. So over here, this is, okay, so here is from 0 to 1. Okay, 0 to 1 right here. Okay, the first time you're going to go halfway. Okay, so you go halfway. So you have 1/2 go over here. Okay, and then after that, you add 1/4. So you go here. So this is 1/2. And now you go forward 1/4. Okay, after that, you're going to go forward 1/8, right? And continue in this pattern. If you add this up, what do you think it's going to approaching to? It's going to approach 1, right? But it's going to take infinite many steps to reach 1. Okay, you get very, very close, but never reach it. So the moral of this story here is never go halfway. Okay, you have to go all the way. Okay, every time you only go halfway here, halfway, you can never reach the other side or the other person on the other side. Okay, so this is the geometric series. Okay, and your guess here is correct. It actually convert to 1. Okay, and we can prove it. Okay. Okay, now this is example of a geometric series. Okay, a simple geometric series. So what is the formal definition for geometric series? It's the one that from one term to the next one, always multiply by a common ratio. Okay, this 1/2 here, in this case, is something called the common ratio. From one to the next, you multiply by the same common ratio. Okay, that's called a geometric series. Now, you can write it in this way. Okay, so the first term will be A. Think about that as kind of like a number, for example, like 1/2. And then the next one you multiply by the common ratio R, so it's A times R. And then the next one over here is you times R again, so AR squared. And then the next one you times R again, that's ARQ, etc. Right? Okay. Now the entrant over here is going to be A times R to the n minus 1. Okay, this is the entrant. Okay. The first one is just R, it's just A. The entrant is A times R to the n minus 1. Okay. Then when you try to write this series over here, you put it this way. So this is the summation. Remember the series. Series means it's the sum. Okay. So you add A, and then you add AR, you add AR squared, you add ARQ, etc. Then you put down the n term, which is the general term over here. Okay. And then n over here go from 1 to infinity. Okay. For example, this one here, n is equal to 1. Okay. If you substitute 1 into n, the 1 minus 1 is 0, r is 0, and it's 1, so it is 8. So when n equals 1 is 8, n equals 2 is 8r. Okay. So you see the exponent here on r is always 1 less than the index, right? Okay. So this exponent here on this r is always 1 less than the index over here, right? Okay. So this is a short notation to represent the series. If you want to write it out turn by turn, you write this the long way like this. If you want to write it in this sigma notation, you write it like this. You put the n chain over here, okay? And then you write down the index go from what to what. The index here starts from 1, okay? And then the 2 and etc. And all the way to infinity, you put infinity here. Okay? So that is two different notation. Okay, this one you list it out. This one is a sigma notation. Now we try to see when can we tell a geometric series converge or not. So we're going to do a trick. Okay. So this is the geometric series, right? From one thing to the next, we keep on multiplying by r, or multiply by the common ratio. So that's a geometric series. And let's consider the n particle, which means we sum up in the first n term. So the first term, and this is the n term. We sum them up. Now what do I do over here? I'm going to multiply that by r, multiply this by r. So a times r, this one here should be what? AR, right? Okay. Now, what about AR times R? So that should be AR squared, right? Okay. And then continue this way. AR squared times R, so that will be ARQ. But what about the last one? If you multiply this by R, what do you get? AR to the n power, right? Okay, good. Yeah, you got it. Okay. Okay, you see this? Now, what I'm going to do here is I'm going to subtract them. Okay, so I'm going to take the top, subtract the bottom. When you subtract them, notice that I line them up in this way so then you can see what happened to the cancellation, right? So if I subtract them, what happened to the chain over here in the middle? What happened to this in the middle? they're going to, are they going to subtract out? Yeah. So this one subtract this, right? Remember you subtract, okay? So they will subtract out, okay? So they will subtract out, this cancel, cancel, etc. Okay, the one here before here is going to cancel with them before. This one here before, this one here is going to cancel with this one here. Okay, anyway, it's going to cancel with this one. Okay, right here, cancellation. Okay, so when we subtract them, okay, so only which two terms here survive?
First.
The first? Yes. Yes, you got it at the first, which is let's see this color. So the first one over here is, okay, is this one, right? This one right here, A, okay, and also what else? Would this one here survive also? Right? This one has no one to cancel it, right? So when you subtract all this middle thing here, it's going to cancel. Okay? So only this one here and this one here survive. But you're subtracting. So you get A minus A on to the n. Do you agree? Uh-huh. Okay.
Agree.
You agree. Okay, great. A minus A R to the n. Okay, you agree. Okay. This one. Now, can we solve for the n partial sum Sn? How do we solve this? You can divide both sides by 1 minus R. This is the n partial sum. That means it's the sum of the first n term. Okay. Now, remember, we talk about the definition for the series, right? So what do we say? We talk about the series over here. If it's convergent, convert to a finite number. If the n partial sum here is converging to a finite number, okay? So you take the n partial sum, which means you take the sum of the first n terms, but you let n go to infinity, which means you consider more and more terms and you sum them up. Okay, and if it approaching to a finite number, for example, this one over here that you have over here, the more term you add over here, okay, then the more the sum is approaching to a finite number and closer to 1. Okay, so if you take the n partial sum and let n go to infinity, which means you add more and more terms. Okay, what's the limit of this n partial sum? Now, before we do this, let's remember the important result we have. Last time I told you guys that we're going to use it later in, right? R to the n, okay? R to the n, when will, if R is between -1 and 1, as n go to infinity, what does it go to? Yeah, it go to 0. Yeah, I heard you. It go to 0. For example, like 1/2, right? 1/2 to the n. You keep on times 1/2, then it's closer and closer to n. Think about you have a piece of maybe string, right? And you take only half of it, and then you take only half of that. The more time you times 1/2, then the closer and closer, then smaller and smaller the quantity, closer and closer to 0. Okay, so then this is 0. Okay, and if R equal to 1, 1 to the n is always what? Always 1. So that will convert to 1. Okay, so that was the result that we have last time. R to the n, if R is between -1 and 1, it converts to 0. If it's 1, it converts to 1, and otherwise it diverges. What does it mean? So suppose R is, say, 1.5. then 1.5 to the n, as n goes to infinity, then it's going to diverge to infinity. Okay, so it only converge when r here is between -1 and 1, and then also including 1, when 1 is converging to 1. Okay, so converge over here and then diverge outside. Okay, okay, now looking at this limit over here is the limit of this n partial sum. When r is between -1 and 1, this one here goes to what? Go to 0. Okay, that go to 0. So therefore, the numerator will this one here go to 0, right? This one go to 0. So you have a on top and then 1 minus r down here. So it converges to a over 1 minus r. So what is that a? Okay. Well, I would suggest that you remember this a here as the first chain. Okay, so this a over here is the first chain, remember? Okay, that's the first chain in the geometric series. Okay, so that is the first chain in the geometric series. Okay. Like that. And then what is the r over here? What's the name for that? R is what? It's the common ratio. Yeah. So that's the common ratio. So if r is between -1 and 1, then the geometric series is going to convert to what a over 1 minus r, which is the first over 1 minus the common ratio, right? Okay. Okay, now let's consider the other case. Okay. The case that when r is equal to 1. Okay. What happens when r is equal to 1? So we know that r between -1 and 1, it converts to this. What about if r is equal to 1? Yeah, when r is 1, let's think about the n partial sum. So the geometric series is like this, right? A, and then the next chain is a times r, next chain a times r squared, and then this is the n chain, a times r to the n minus 1. So when r is 1, this is a, right? And this one will be what? A times 1, which is just a, right? And then this is, all of them will become just a. Okay? So they're all a. Okay, we get all a. Okay, so Sn will be what? Not 1. Na, yeah, Na. Okay. Na, as n go to infinity, what does it go to? Is 1 your favorite number? Not 1, not 1. Okay. And I heard Gloria say infinity. So if a here is positive number, it certainly go to infinity. If a is a negative number, it go to what? Negative infinity. Yeah. So in any case, it doesn't go to a fixed finite number, right? Okay. So if it doesn't go to a fixed finite number, the series converge or diverge. Diverges. Yes, diverges. Okay. So if r equal 1, it diverges. Okay. How do you get this? Okay. All right, let's go for this. So the r here is 1, right? So r is 1. So 1 times a is what? A. R squared is also 1. A times 1 is a. So 1 to the n minus 1 is 1. A times 1 is a. But how many a do I have? The first entry. I have n of them. So I have n times a. Right? Now, depends if this a is positive or negative. If it's positive, then an n goes to infinity, that is going to go to positive infinity. For example, suppose this is n, suppose the a over here say 1/2, right? Then what happens if you multiply by n? That is going to go to, when n goes to infinity, this is going to go to wait, try again. Okay, 1/2. Okay, this one here go to infinity, and then multiply by 0.5. That will go to that will go to infinity. Yes, that will go to infinity. Yes, okay, that will go to infinity. Okay, if the a here is a negative number, say negative, so say negative 3. Okay, and then multiply this by n. As n go to infinity, it go to negative infinity. So in any case, it doesn't go to a fixed finite number, right? It's not a finite number, okay? So therefore, the series diverge, okay? Diverge just means it doesn't go to a fixed finite number, okay? So if it's infinity or negative infinity, that's not a finite number. Okay, now after this, let's put this together, okay? The important result that you want to remember is this, okay? So this is an important result right here, okay? So for geometric series, okay, so first of all, I want to explain maybe the name, why it's called geometric, okay? So if you have this right here, you see this square, it's a by a square. And if r is between 0 and 1, so a times r is a portion of the side, okay? So that's AR. And then you construct a square over here again with AR as a side. If you times r squared, this is AR squared. If you times r again, this is AR cubed, etc. And looking at this right here, a plus AR squared plus AR cubed, etc. Keep on going. Okay, it is the length of this to this. Okay, it converts to this. And how long is this length here? It is, okay, can you tell me? Remember here, R here is between 0 and 1, okay? Then S, yeah, it is S. And S, what does it equal to? It converts to A over, yes, you got it. A over 1 minus R, yeah. So it converts to A over 1 minus R. Okay, A over 1 minus R equal to that. Okay. So we actually know how long is this one. Okay. So so this is kind of, so that's the name where I call geometric series. I think it has this geometry in it. Okay, geometric series. Okay, like that. Okay, now we just did the investigation. We say that geometric series over here is convergent if R is between -1 and 1. Okay. For example, like R is 1/2, R is 1/3, R is -1/2, or R is -1/3. Then the geometric series here is going to sum up to a finite number. And we actually know what does it sum up to. It sum up to the first term over 1 minus the common ratio, A over 1 minus R. Okay, think about that as the first term and 1 minus the common ratio. And otherwise, if it's not from -1 to 1, then that geometric series diverge. Okay, so it doesn't convert to a finite number. Okay. How about we do some example? Okay. So in short, this one just say that geometric series converge if and only if the absolute value of the common ratio is less than 1. Okay. So are they doing it again? So this is the common ratio. So if the absolute value of common ratio is less than 1, then the geometric series converge. Okay. If it's not, then it diverge. Okay. Let's look at this example here. Is this a geometric series? Well, what is the common ratio? Can you see a pattern? Okay, phi, you can think about it as phi over 1, right? We can think about it as 5 over 1. Okay, let's look at the denominator. 1 to 3 to 9 to 27. And you keep on multiplying by what? 3. Multiply by 3, right? Yeah. So multiply this by 3. And then times this by 3, right? Etc. Okay. All right. Good. Okay. What about the numerator? 5, 10, multiply by 2. Right. Keep on multiplying by 2. So that means you're multiplying by 2 over 3. But also notice what happened to the side. The side alternate, right? Sometimes positive, negative, right? Alternate. So what's the common ratio then? It's negative 2 over 3. Yes. So the common ratio is negative 2 over 3. You got it. Good job. Okay. Yeah, because alternating side. So when the common ratio is negative, every time you multiply by that, the side alternates, right? And then the 2 here will come to this and 3 come to this. And the side alternates. So that's why it's negative 2 over 3. Okay, now let's take the absolute value of this common ratio, which is equal to 2 over 3, right? Comparing to 1, it is what? Less than 1. So according to the result we just found, right? This one, this geometric series is convergent or divergent? Converge. Okay, so it converge. And what does it converge to? First one is 5. Yeah, you got it. And the common ratio is negative 2 over 3. And to the algebra, yeah, it should be 15. Wait. It's not 15. It's 3. Okay. Yeah. Because this one here is minus 2 over 3. So this is going to be 1 plus 2 over 3, which is what? 5 over 3. 5 divided by 5 over 3 is 3. Okay, so the result here is 3. You see it? Okay, so we know that if you sum up in all the terms, okay, well, there are infinitely many terms, okay, you can never sum all of them up, but however, as you get more and more terms, the result get closer and closer to 3. So we say that this series here, it converts to 3. Kind of interesting. They alternate. So it's kind of like maybe the things like this. So you have 3 over here, right? But then it's going to go some alternate, because the alternate side, so it go like this. I think it go like this, and getting closer and closer to the sum. Okay. Okay, so that's good. So let me think. What about this series over here? Is it I said it's a geometric series, okay? But let's find out what's the common ratio. Let's find out the first couple terms to get a feel of the series. From here to here, what do you multiply? From one term to the next. What happened to the exponent on 2? Right? This one is 2 to the second. This is 2 to the 2 times 2. This is 2 to the 2 times 6, right? So 2 to the second, 2 to the 4, 2 to the 6. So multiply by what? 2 to the second. Yeah. So multiply by 2 to the second first. Okay, now let's look at the exponent on 3. Okay, let's look at this one. What happened to the 3? It go down, right? 3 to the 0, 3 to the negative 1, 3 to the negative 2. So it is going to be multiplied by 3 to the what power? Negative 1. Negative 1. Yeah. This one here is 3 to the 0. Yeah. This one here is 3 to the 0. Right? This one here is 3 to the negative 1. This is 3 to the negative 2. So every time you multiply by 3 to the negative 1 power, so 3 to the negative 1 power is the same as 1/3. Okay? So therefore, you keep on multiply by 1/3. Okay? All right. And then, yes, so same with this one. Okay? Now, from here, you figure out the common ratio. So you should be able to write down that this notation using the sigma notation to write this geometric series, right? This is the general form of the geometric series, okay? So is A times R to the n minus 1. Okay, what's the A in this case? A is the first term. What's the first term? Okay, this is the first term, right? Okay, so this is the first term. So that is what? 2. Yeah, that will be 4. Yes, that's 4. You got it, 4. Okay. And then what's the common ratio? R. 4 over 3. Yes, you got it. 4 over 3. Good job. Okay. All right. It is indeed a geometric series, right? Okay. With this common ratio. This geometric series converge or diverge? What's the diverge? Well, what's the reason? Yeah, it is greater than 1. So it diverge. Okay. It only converge from negative 1 to 1. If it's outside, then it diverge outside. Okay. Okay. Now another way to see this geometric series over here to convert, instead of writing out the first couple terms, you can actually use algebra. Okay. How can I convert this into this form? Okay. Now the first one here is this one has 3 to the 1 minus n. So it's the same as, okay, let's write down. 3 to the 1 minus n is the same as 3 to the opposite of n minus 1, right? Okay. And that way, this one here is equal to, when you have this negative sign here, that means reciprocal. So that's the same as 1 over 3 to the n minus 1. And that's why this one here is this. Okay, so that's how we got that. Okay, so we write this. Okay, so 3 to the 1 minus n. If you put that in the denominator, that will be 3 to the n minus 1, the opposite of it. Okay, and then 2 to the 2n power is the same as 2 to the second power, which is 4. So 4 to the n power. Okay, so if you have a question about that, let me write it down. So 2 to the 2n power is the same as 2 to the second power and then to the n power. 2 to the second power is 4, so it's 4 to the n power. Okay. So you write this as 4 to the n power. Okay, this one right here. Now, after you have done this, you want this to be in the form like r to the n minus 1 power. So this is n minus 1 power. You want to break this down into 4 to the n minus 1 power times 4. Now, when you do that, this over that is a common ratio, 4 over 3, right? So you get 4 over 3. to the n minus 1 power. And then you leave the 4 here outside. Okay. So you can convert that using algebra. Okay. So there are two different approach. I guess many of you might find the first one lists out the first couple terms to see the pattern a little bit more straightforward. This next one here is use more algebra to do it. Okay, involve doing those exponent law and etc. Okay. Okay. Any case, we know that this geometric series diverge because r is greater than 1. Okay. Now, how about we try to use some example to see the geometric series converge or not. Okay. How can you check if the series is a geometric series? Well, if it can be written in a form, in this general form, the series of a times r to the n minus 1 or a times r to the n, then we know that it's a geometric series. Okay. And with the common ratio here to be r. Okay. Okay, let's look at this one. What is the common ratio? What do you keep on multiplying? What's the R?
0.2?
Yeah, it's 0.2. Okay, good. Yeah, it's 0.2. Now, if you had hard time figure this out, you can try to use the next term divided by the term that's right before it, right? So this divided by that, or this one divided by that, all of them will equal to 0.2. So you just take the next series, divide by the term that's right before it. You can figure out the common ratio of this. Okay? So this divide by that 0.2, this divide by that is 0.2, all of them. The common ratio is 0.2. So the common ratio is 0.2, the series converge or diverge? It converges. Okay, good. Because it's between 0 and 1. Okay, so it converges. Okay, the next one here. What's the common ratio? 0.7. Converge or diverge? It converges. And I'm going to put CONV, con, for convergence, okay? Short for convergent. Okay, next one here. Can you rewrite that in this general form, right? I can put a 2 here, and then this to the n power. What should I put in this parenthesis here? E to the negative 1. Yeah. So, Diana say this is 1 over e to the n, so it's e to the negative n. So this should be 1 over e, right? Okay. So 1 over e, okay. Because 1 to the n is 1, e to the n is e to the n down here, right? So this and this are equal, okay? So R here is, what's R? What's the 1 over E? E is about 2.7. Is this number here between 0 and 1? Yes. So convergent or divergent? It converges. Okay, so it converges. Good. Okay, the next one you can try first. Figure out the common ratio. Now to match with this exponent n minus 1, I'm going to break this n as 1 plus n minus 1, right? So this, you can write it as 5 times 5 to the n minus 1. So this will be 1 over 5. 1 over 5 times, what's the common ratio here inside? Negative 3 over 5, right? Okay. So let me highlight this for you. Okay. So negative 3 over here over 5 over here is this common ratio. And then this 5 here is from this. Negative 3 over 5 is this common ratio. They both have exponent here to be n minus 1. Okay, so put it like this. So R is equal to negative 3 over 5 this geometric series converge or diverge? It converges. Yes, you got it. Because it's between -1 and 1, and so it converges. Okay, good job. All right, question. This one over here is also a geometric series, right? It doesn't look like the one that we saw before because it's not just number, it has the variable x. But let's think about from one term to the next, you'll keep on multiplying by x, right? So the common ratio is what? What's the common ratio? X. Yes, you got it. So the common ratio here is the x, okay? And if you want to write that in the sigma notation, so you can put x to the n, okay, the n term over here. However, the index here, n doesn't start from 1. Because this one over here is x to the what power? You can think about that as, yeah, it's x to the 0 power. Okay, x to the 0 power. So n start from 0 to infinity. Okay, so not starting from 1. This is a geometric series. Okay, and when will this geometric series converge? Converge if the absolute value of the common ratio is what? Less than 1. And we know this is the common ratio, remember? Okay. So if absolute value x is less than 1, then it converge. Okay. So, and what does it converge to? First term over 1 minus common ratio. What's the first term? 1. Yes, you got it. 1. And 1 minus what? X. Yeah, you got it. So it actually converges to 1 over 1 minus x. Okay. So this result here is worth remembering because we're going to use it again and again later in the semester. Okay. So this geometric series is going to converge if and only if the absolute value of x is less than 1. What does it mean absolute value x is less than 1? That means x is between what and what? X is between what? How do you get absolute value x is less than 1? X is between -1 and 1. Okay, something. Okay. So if you have absolute value x is less than 1, okay, if x is between -1 and 1, then this is going to equal 1 over 1 minus x. Okay. Well, maybe let's try some example. Okay, let's try some example. Put some number here. Okay, example. Suppose we have this series over here. So this is x here is a -1, right? Maybe I should be consistent, use the same color. -1, right? And then to the n power, and go from 0 to infinity. Okay, so I replace this x over here by -1. The absolute value of that is less than 1. Okay, and this one here converge or diverge? Converge, and what does it convert to? You got it. 1 over 1 minus -1, right? And then you can do the algebra for that. Okay, all right. So remember, in order for this geometric series to converge, x here had to go from -1 to 1, not including the m point. Okay, it has to go from -1 to 1 in order to do that. So now there's a geometric series. Okay, let's talk about telescoping series. Okay, so the geometric series, think about the common ratio. Now, telescoping series, this is an interesting name. Where does the telescoping here come from? You're going to see where this name comes from. Okay, so first of all, I want to ask you guys, does this series here converge and why? Well, take a guess. If it converted that way, no idea. Okay, we don't know yet. Okay, let's investigate a little bit. Let's figure this out together. Okay, so in order to see a series converge or not, you look at the n partial sum. Remember, you try to look at Sn. You look at the sum of the first n term. Okay, and then you let n go to infinity. Okay. Now this an over here is kind of special. It's 1 over n times n plus 1. Do you guys remember partial fraction decomposition? Right? You can decompose it, right? Now, at that time, we do that for integration, right? So we use partial fraction decomposition, we can decompose it, okay? And let's review the process of the partial fraction decomposition. How do we do this? So this is the denominator factor into n times n plus 1. So the two partial fraction here will have what? One of them has n, the other one will have what? N plus 1. And up here you put what? Number, right? You put number, okay? So a and b. Now, how do we figure out this a and b? You multiply both sides by the LCD first, right? Multiply both sides by the LCD n times n plus 1, what do you get? On this side, you get 1. Okay, on the other side, you get what? A times n plus 1 plus b times n, right? Yeah, you got it. So when you use this times that, the n here divide out, so you have n plus 1 here. When you use this times this, the n plus 1 divide out, so you have b times n here. So you got this. And from here, you try to figure out the a and b. Then the two methods. One method is to try to plug in special value of n. Those n will be the zero of this. What is the zero of this denominator? What are the zero of the LCD? This is the LCD. What is this? 0 and -1. Yes, you got it. So 0 and -1. And let's plug this in. Okay, n equal to 0. N equal to 0. This one here, right? This one here is going to disappear because 0 times b is going to disappear, right? So when n equal to 0, this one here is gone. And then this one here will get what? 0 plus 1 plus a, which is just a. So a is equal to 1. So a equal to 1. Can we figure out the b? We're going to plug in what? N equal to -1. Yes. All right. So plugging n equal to -1. Then what happens here is this here is going to be gone. So -1 plus 1 is good. This is gone. So you will have -1 times b equal to 1. So what is b equal to? -1. Yeah, you got it. Okay. 1. So you figure this out. So this is one method, okay, to do to figure out a and b. So once you do that, then you know that this is going to be decomposed into 1 over n minus 1 over n plus 1. Okay. Now, after a while, you actually see a pattern. This equal to this. Okay. 1 over n subtract 1 over n. Let's write down the first n chain. Okay. So the first chain will be, the first one over here is this a1. Okay. So what is this a1? A1 is 1 minus 1. Okay. So this is A1, right? Okay. And what's A2? This is A2, right? And this one here is A3. Yeah. So A1 is going to be 1 minus 1 half. When you substitute 1 in it, so it's 1 minus 1 half. And then A2, substitute 2 in it, so it's 1 half minus 1 whole. The A3 substitutes 3 in here, so 1/3 minus 1/4. And you see the pattern, right? Continue this way. Okay. So this is the series. And if you look at the n partial sum, So we're going to stop at an. An is this. What happened to this one and this one? This one, this one, this one, this one, this one, that one, cancel. This one is going to cancel with the one that is y before it, right? So what's the y?
1.
1 minus 1 over x plus 1, right? Yeah, good. So we're going to left with that one. Okay. Now tell me, when n goes to infinity, what does this go to? Wait a minute. This one, either 1 or 0, right? I think that's a good chance. Okay, if you say 1 or 0, okay. Okay, so that will be 0. Okay. So when n goes to infinity, the denominator go to infinity, and then 1 over that is going to go to 0. Yeah, that goes to 0. So this whole thing goes to what? See, this time is 1 is right. Okay. Okay. Well, I figured that in math class, a lot of time you can say 1 or 0, 1 or 0. That's true. Okay. So that's equal to 1. Okay. Okay. So the limit of the n positive sum is equal to 1. So we say this series here is going to convert to 1. Okay. So we say that this is equal to 1. Okay. Equal to this right here. Okay. It's the limit of the n positive sum is the sum of the series. Okay. So we say this telescoping series convert to 1. Okay. Now I'm going to tell you, I draw the picture. Actually, I took this picture of the internet. Okay. I took an old style telescope. Okay. And you see those old style telescope look like this. How does it work? They can collapse, right? Do you have that at home? No, you don't have that at home. I don't have it. But we see that in the movie sometimes. Okay. So what happened? You can actually collapse them, right? So the telescope like this, you can see far away, and then you can collapse and make it shorter, right? So when you collapse like this, only the first and the last one here you will see, right? So kind of like this one here. So when you take the n positive sum, then the middle part here gonna collapse like this old style telescope. Only the first part here and the last part here is a y. So that's why it's called telescoping series. You see the name? Okay. So that's the one. Okay. Now, would that example is the only telescoping series? That's not the only telescoping series. Okay. We have over here is another example of a telescoping series. Okay, this one. Okay. At first you say, how do I know it's a telescoping series? Okay. How do you know? Well, you first do what kind of thing first? We need to do the partial fraction decomposition first, right? So when we do the partial fraction decomposition, and then I come up with this. Okay, so from here to here, then you do the partial fraction decomposition. Okay, you got this one. Okay, and then what do? You write down the sum of the first n term, the n partial sum. So you substitute. What do? So you substitute 1 into it, right? Substitute 1 into it, we got 1 4, and then minus 1 half minus 1 4. The first one. Substitute 2 in the I. So that 1/3 minus 1/5. Substitute 3 into I. 1/4 minus 1/6. Okay. And then for the n term, it's going to be this one. 1 over n plus 1 minus 1 over n plus 2. But what's the term that's y before this? The term y before this is 1 over n minus 1 over n plus 2. Okay? And then you see what are the canceling here? Do you see the canceling? This one here is going to, that is going to cancel with, well, not the one that's y after. Not the one y after. It's actually here. This one cancels with this one. So sometimes it's not the neighbor. It's someone that's further away from you. Okay. So this one here cancel with this one. Okay. What else? And this one over here cancel with which one? Right after this, right? There's something over here. Okay. So it's going to be, you're going to go skip one turn and will be the one that is right after this next chain. You're going to cancel with it. Okay. And taking a look at this pattern, you're going to see all the chain here is going to cancel. Okay. Say, for example, like this one is going to cancel with, this is going to cancel with something that is one. Okay, think about this. There's a one chain right before that. Then it's going to cancel with one chain over here. This one and the chain that over here, they're going to cancel. Okay, these two cancel. Okay. And then this one over here going to cancel with not this chain, it's the chain before this. Something maybe here, then there will be something over here. Okay, will cancel. But in any case, you see that in the middle here, the chains cancel, and you see what survive over here. Okay, it's important to keep an eye on those survivors. Okay, who survived? Okay, so who survived this? This one survived, right? Do you see? That one survived. What else survived? What else doesn't get cancelled? One third, right? Didn't get cancelled. Okay, and then the middle here cancel, and what else? This one. This one, if you need canceling, you need to skip one turn and go to the next, but you stop right here. This is SN. So this one here survive, and then also this one survive, right? Okay. So when you do that canceling, all this green part here survive. Okay, they don't get canceled. Okay. So we write it down over here. Okay. Now as n go to infinity, what happened to this one and this one? What does it go to? Yeah, they go to 0. Okay, that's the important part. So they go to 0. So the whole thing go to 5/12. Okay, and we say the series here converge to 5/12. Okay, so this is another telescoping series. Now I'm going to give you guys some observation. How can you tell a series here is a telescoping series? There's no clear-cut guideline. Okay, there's something that can suggest that it's a telescoping series. So if that can be factored, if the numerator can be factored as n plus an integer and n plus an integer, if these two are different by integer, then there might be a chance that could be a telescoping series. And how can you check? Then you use partial fraction decomposition and you write out Sn and see if they cancel in between. Okay, so check it out. So for example, this one. See, this is n plus 1, right? Okay, you see the denominator, n plus 1, this is n plus 3. And up here is the number. Okay, up here is the number. Then you're going to do the partial fraction decomposition, and you can decompose it this way. Okay, and then you write out the sum of the first and 10 and see if they cancel. You check if they cancel out or not. Okay, and you see that 1 and 3 are different by 2, different by integer. So that suggests that maybe I can write that in using partial fraction decomposition, and maybe they will cancel in the middle. Okay. All right. So that's one observation that I have. Another observation here is sometimes if you do the partial fraction decomposition, for example, like this one here, the denominator is what? This is n plus 1 times n plus 2. They are different by 1. When I do the partial fraction decomposition, it turned out to be this plus this. Do you think it's going to cancel in between? Yes or not? It's not going to cancel in between because you see that in order to cancel, this one here has to be what? Subtraction, right? Okay, so you have to have a subtraction in between, so then later when you add, they can cancel out. But what do you have over here? This is a plus sign. Definitely it's not going to cancel, okay? So this one here, even you can decompose it using partial fraction, there's no canceling happen because the plus sign right here, okay? Now, we're almost done with this. So for your homework, there's something like this, okay? This is, again, a telescoping series. How? You see right here, if you write down that, you can see that there's some, the middle one is going to cancel. Write down the sum of the first and 10. This one over here, what can I write this as? I can put 5 here. Ln of a quotient is the difference of Ln of what and Ln of what?
And Ln and
Yes. So when this is a quotient right here, Ln the quotient, you can change into Ln of the numerator. In this case, it is n, right? This n over here. Subtract Ln of the denominator. In this case, is n plus 1, right? Now, by doing this, if you write down the sum of the first and 10, because the subtraction here, you're going to see that, also because this is n and this is n plus 1, you will see that there's some canceling in between for the Sn, okay? So that's, remember this when you do homework, okay? All right, let's take a 10-minute break.